The components of a software architecture that is at the heart of the software high-level design are meta-architecture, software architecture, guidelines, and policies. Let's take a closer look at these three components. First, meta-architecture is a general guideline for designing an architecture. It is a set of general decision trees and design patterns for defining the architecture of the software, the style, the role of the architect, and consisting of templates for the architecture documents. Next, the software architecture consists of 4 views: module view, component and connector view, allocation view, and code view. Also, as a result of the architectural design, the context diagram, component specification, and interface specification must be derived. Let's take a look at what you should know when defining views. There are many different ways to define views for each person. Description method, diagram shape, box, line, etc. are all different. Therefore, we only need to consider the selection criteria and notes when describing the view. Also, there are usually 3 views such as module view, component and connector view, or allocation view. In addition, code view can also be added here. When you define each view, you must describe at least a view. And how many views are appropriate depends on factors such as the competence of the developers, the understanding of the domain, the experience of the previous project, and the major issues. It should be the basis for judging quality attributes such as systems big function, availability, changeability, security, and performance. And the functionality of the key module should be described how they are related to the inside-outside. Also, you need to be able to figure out the size and scope of your system. Finally, you should be able to describe the rationale for building the architecture description. In previous versions of UML 1.x, these views were difficult to represent. This is due to the design of excessively technology-dependent patterns or components mainly created at the deployment level. When building UML 2.0, OMG has much adopted the architecture definition from the Carnegie Mellon University SEI so as to make it easier to describe these areas. Next, guidelines and policies are that they are for determining the software architecture and then conduct the project based on the defined architecture. Architects should describe and make a decision on a comprehensive set of development policies with guidelines and policies for design, coding, deployment, integration, testing, tools, maintenance, system expansion, and system operation. These software architectures relate to the various components of system development. Project organization, project schedules, and configuration management plans are based on software architecture. The utility programs, prototypes, and frameworks affect software architecture design. Now, I will explain the role of the software architecture and its relationship to the development process. The software architecture has the following roles in system development. First, it becomes a means of communication between relevant stakeholders. Second, it is a tool to make decisions early in the development project. In particular, as it determines the quality factor, it has an overall impact on the project organization. Third, it determines the overall structure of the system. Fourth, it affects to determine the organization of the development project. Fifth, it determines the quality factor that the system should have. This allows the architecture to predict what quality the system will need and what quality it will have through the architecture. Sixth, you can decide what curriculum and training content delivered to system developers through the architecture. Finally, it informs the process or workflow how to manage changes to the software. Let me explain how software architect plays a role in the overall development process. Functional and non-functional requirements act as inputs to design the software architecture. Once the software architecture is determined, you can design your software using design patterns and design guidelines. Once the software architecture is determined, coding standards and guidelines can be provided when writing codes. And the software architecture provides guidelines for deploying software on the system. With such repetition, this allows you to build a structured, stable software architecture. Now let's look at the types of software architecture. We will group each type into data flow group, call return group, data-centered group, and event system group. First is the data flow group. Types included in this group are types that can achieve reuse and changeability. This includes the batch sequential processing, type, and filter types. For the batch sequential processing types, the components are independent programs. Each step must end before starting the next step, and data in each batch step has the entirely moving characteristic between steps. Let's look at the pros and cons of pipe and filter types. First, the pros are easy to understand the data flow control process, having specialized analysis functions, enable filter reuse, achieve concurrency, and easy to maintain and expand. In contrast, there are cons in that it is not suitable for highly interactive systems, difficult to maintain consistency between many relevant data, increases complexity, and can cause the performance issues. Next is the call return group. Types included in this group can achieve changeability and scalability. This includes layers, main programs and subroutines, and object-oriented types. First, the pros and cons of layer types. Pros include providing a design based on abstraction levels, improving scalability, providing high reusability and portability. The cons are that it is difficult to apply to all systems, and in some cases it can be very difficult to find the right level of abstraction. The following are the main program and subroutine. It has excellent reusability and ease of system evolution. However, components have the cons that they have to give up control over the calculations that the system processes and require careful handling of the data. Next is the pros and cons of object-oriented types. Implementation is easy to change, and there is in pros that design of problem area analysis is intuitive. But you have to know the identifiers of other objects, and you have to modify other objects when you change the object identifier. Next is data-centered group. The types contained in this group are used when data is concentrated in the system and multiple clients interact with the system to obtain the data. The components are centralized data repository and data-consuming client. Here are the storage types and Blackboard types. The repository is a passive data center, a type that checks to see if a client needs to fetch data. A Blackboard is an active data center, a type that notifies changes to relevant clients when data changes. Next is the event system group. The types contained in this group are aimed at achieving changeability by eliminating the dependencies of various parts of the process through independent processes or objects. This includes implicit call types and explicit call types. For the implicit call type, a component is a module with an interface that provides a collection of procedures and a set of events. Also, it connects to event registration and procedure call. As a constraint, the event provider does not know which components are affected by the event. In case of the explicit call type, every time a system function is changed, the other module that imports the module must also be changed. In addition, reflection provides a mechanism to change the system configuration or behavior at any time of execution, MVC and PAC, which allows the system to respond flexibly to changes by sharing responsibilities. Brokers provides distributed transparency in a distributed environment. Microkernel types divide the system into core parts and change parts to accommodate frequently changing requirements. The purpose of structured high-level design is to develop a modular software architecture based on specifications developed through structural analysis. In software architecture, two big actions must be described. First, decompose the system into modules that provide clear functionality. Second, describe how the decomposed modules integrate and interwork together. In particular, various items must be organized to describe how to integrate and interwork. First, it develops a module interface that defines the module's components that can be used externally. For a typical embedded system using the C language, functions that can be called from other modules, global variables that can be assessed, data structures and macros make up the module's interface. It also determines the usage criteria for various resources, such as error handling criteria, threads, timers, interrupts, and alarms shared within the overall modular structure, and technology standards, such as the data types that are shared on the development platform, are determined. Although various techniques can be used to describe such a module structure, the structural high-level design methodology is divided into a task structure design, which shows dynamic aspects, and a module structure design, which describes static aspects. Task structure design step identify the tasks that can be performed simultaneously on the system based on the output of analysis, and describe the dynamic aspects of the system. Module structure design phase identifies modules that are development units based on output of analysis and task structure, and specify technical standards and module interfaces. We will continue to explain the process of high-level design based on the structural analysis results of the automobile cruise control system presented on the screen. The task structure design shows all the processes identified in automobile cruise control, as you can see in the figure. The figure is an example for describing the task identification process, not the regular output created in the development methodology process. This figure shows all the processes identified so far, showing that the patterns are asynchronous, periodic, and control. Let's look at the procedures for a task structure design. In the structural design methodology, the task structure is designed according to the 3 steps task identification procedure proposed by Hassan Gama. The task identification procedure consists of 3 steps. Task candidate identification is the identification of processes that require their own execution. Remaining process allocation refers to allocating processes that have not been assigned their own tasks to task candidates. And task integration means integrating task candidates within a time constraint. Let's take a closer look at each of these 3 steps of task identification procedures. First, let's look at identifying candidate tasks. According to the technique described, processes according to the asynchronous, periodic, and control patterns become task candidates. The table lists the identified task candidates. On the left are task candidates, processes in the middle, and criteria for selecting them on the right. Next is the allocation of the remaining process. The figure shows how the process identified as remaining processes in the automobile cruise control example are distributed. The figure shows how the 4 tasks that were not identified in the previous step are assigned to some task candidates. The table lists the processes that have been allocated and their criteria. Task candidates include Task 3 and Task 4, and the processes allocated to them have processes determine the speed, and there are processes related to the preemption of the expected speed. In addition, each process is mapped to task candidate according to the degree of sequential cohesion and control cohesion. Next is the merging tasks. Automobile cruise control example shows the cases where task integration is possible as per the table. The table shows which tasks have been integrated, how they were selected, and the criteria definition. For example, you can see that Task 1 and Task 2 integrate due to functional cohesion. That is, mutually exclusive execution characteristics. We will complete the task structure of the automobile cruise control system through task candidate identification, remaining process allocation, and task integration. The completed task structure is the same as the screen. In figure, the diamond indicates the identified task, and the line between the tasks indicates the flow of information required between the tasks. Each of these tasks consists of processes presented in the screen. In the table, you can see how each task is mapped to each process and how they are composed or connected to each other. Now, let's look at high-level design method by object-oriented methodology. In general, the object-oriented development methodology does not have a clear boundary between object and behavior analysis and object and behavior design. Therefore, the object and behavior analysis models are refined to a more sophisticated design model that matched the selected software description, and detailed implementation description is established. In this case, the object and behavior analysis model evolves into a design model. During the high-level design phase, developers perform activities to describe the system in terms of logical software architecture and determine the implementation strategies to implement the system in terms of client-server architecture. First, let's look at logical software architecture determination activities. This activity refers to the activities of layering and decomposing the system to have a low degree of coupling. The main goal of this software architecture determination is to minimize the scope of change at the logical architecture level, not at the unit class level. As minimizing the scope of change is closely related to software scalability and maintenance, the coupling issue must be solved well in terms of logical architecture. In principle, the lower the degree of coupling, the easier the software is to expand and maintain. And in a software architecture with a high degree of coupling, a change in a particular part will impact changes in other parts that depend on it. Determining the logical software architecture to decompose these systems is executed regardless of the implementation strategy. The following table summarizes the activities briefly for determining logical software architecture. I will continue to explain vertical layering and horizontal decomposition. Vertical layering is the packaging of boundary classes, control classes, and object classes shown in class diagrams and placing them in a vertical hierarchy. I will explain them through the picture. The picture shows a layered architecture that is packaged vertically into 3 groups for the depositor service system. Boundary classes are packaged as GUI groups from class diagrams created in behavior and analysis activities. Control classes are also packaged into workflow groups. You can see object classes are packaged as domain groups. In this example, the dependency represented by the dotted arrow indicates that the higher layer uses the lower layer service. Next, horizontal decomposition can be performed to reduce interlayer coupling when certain layers are complex. In addition, the classes in the same layer can be performed by the developer's intuitive criteria or a systematic analysis method. Let me explain with the example. The figure is an architecture in which the domain group hierarchy, previously discussed, is decomposed horizontally again. Classes with similar functionalities are grouped together. In other words, horizontal decomposition was performed to increase the functional cohesion and have the grounds that customer management and account management aspects can be functionally separated. This time, I will explain subsystem decomposition. Like layering and decomposition, client and server architectures are also logical concepts. In other words, from a software development perspective, a client-server architecture can be realized on the same hardware platform or on different hardware platforms. The example on the screen shows the software development architecture for fat clients and thin clients, assuming the package of vertical layering architecture as discussed above are deployed on different hardware platforms. Looking at the first fat client, each client consists of GUI group, workflow group, and domain group, while thin clients consist of server, workflow group, domain group, client, and GUI group. The figure on the screen is a subsystem architecture diagram decomposed into subsystems according to the previous activities. The left side is the subsystem architecture of fat client, and the right side is the subsystem architecture of thin client. Next, the technology environment definition will determine the technology environments for the client and server subsystems and may include technology selection for any middleware that connects the client and server. In other words, When decomposing a subsystem into a client-server architecture, developers must choose the most appropriate implementation technologies. To do this, they will determine the technologies for object-oriented programming language, operating system, middleware, user interface development tools, and database management system. Currently, technology environments that support an object-oriented paradigm are very broad and constantly evolving into or trends of rising new technologies. As technologies to implement object-oriented methodologies are too broad, the high-level design, a specific development language, specific middleware, specific user interface implementation techniques, or a specific database management system is not willing to be confined with specific one just like all object-oriented methodologies. Therefore, after selecting the technology environment, the design phase should be dependent on the developer's expert knowledge and specific technologies. The figure on the screen is a client-server architecture from a software deployment perspective. A client or server has a separate hardware platform and shows typical technologies required to implement software with a client-server architecture. This picture shows a web-based software architecture deployed on 3-tier hardware platforms. It demonstrates the core skills required to build a web-based system. A web-based system is an extension of a client-server architecture with a website, where the business logic can place on the server side or client side. Next, let's look at subsystem interface design. Once the subsystem decomposition and the technical environment are established, the interface to the derived subsystems starts to be designed. First, this example assumes the following scenarios. Assume that you have assigned the workflow group package and the domain group package to the application server, as shown in the thin client architecture and the diagram of first technology environment. It is also assumed that the interface technology between thin client and application server uses remote method invocation, RMI, provided by Java. Then, this will require a subsystem interface design to use remote method calls between classes belonging to GUI group and classes belonging to workflow group. The figure on the screen defines the interfaces that classes belonging to workflow group provide to the classes belonging to the client subsystem. The user interface is defined as the interface between the person and the system, or the information channel between the user and each system. Therefore, to make the system more easier to use, user interface design means to identify the problem of information exchange between user and system, then systematically design to resolve, implement, and test them. Especially in modern times, in an environment in which a computer directly or indirectly occupies a large part of our lives, the interface between the computer and human being is becoming an important issue than anything else. During development of the system, there is a statistics that 80% of the overall maintenance costs are related to the UI. In addition, Jacob Nielsen, author of Usability Engineering, predicts that if a better navigation system is not built and a rigid internal design standard is not enforced, the cost of bad usability of intranet usage will be exponentially increased in worldwide. Zona Research estimates that e-commerce companies are losing more than $58 million a month from frustrated customers due to web pages. Therefore, the UI process must be applied from the beginning of system development, and the ideas that shortening the development cycle, meeting the user requirements, increasing the usability, and helps to generate a bigger business profits are spreading. The following is a summary of 8 ways to design a great user interface. It is necessary for the design of the user perspective, so please refer to them.